Hi everyone, in this video we'll be talking about proving continuities and differentiabilities. So to prove that a function at a certain point is continuous, we have to satisfy three things. We have to satisfy three things. First thing is that lim as x approaches h is being the point that you're trying to prove is continuous or not, exists. Second, you have to say that lim as x approaches h from the left has to equal to the limit as x approaches h from the right. And third and finally, lim as x approaches h has to equal f of h. So the limit has to exist, the limit has to be equal from on the left and right side, and the function has to be, the function at that point must be equal to the limit at that point. So, whoopsie. What did I just do? Okay. And then lim as x approaches h must equal f of h. So these two technically prove each other, but you still have to write all three of these down to state that the function is continuous. So let's take a look. Let's take an example over here, right? So at this point, the function is obviously not continuous. So why? The limit. Does the limit exist? The limit does not exist as it goes towards infinity. Although the left limit and the right limit are the same because they both go to negative infinity. The limit does not exist because it's infinity. So we call this an infinite discontinuity. Okay. And then if we move on to the next point, this point is also not continuous. Let's see why. Does the limit exist? The limit exists at h. But does the left limit and the right limit equal to each other? They do not. The right limit is positive while the left limit is negative. So this point is not continuous, and this is called a jump discontinuity. Jump discontinuity. I'll try discontinuous. All right. Now let's take a look at this point. This point, the limit from the left, and the limit from the right is not equal again. So this is another infinite discontinuity. And finally, let's take a look at this point. The limit exists, which is this point, so number one is satisfied. Number two, the limit from the left and the limit from the right are both equal, which approaches this point, which is also right. So both of these are satisfied. But the third one is not satisfied because this point, f of h, let's call this point h. Alright, let's call this point h. F of h is a positive number over here, whereas the limit is actually approaching this number, down here. So this is not continuous again, and we will call this, what just happened? We'll call this a removable discontinuities. So this is a removable discontinuity, this is the jump discontinuity, and these two are infinite discontinuity. Let's look at any other point. Let's say this one, alright? The limit exists, both, and they're approaching this point from both sides. So the first two is already satisfied, and third one, the point f of h at this point is equal to the limit. So this is why this point is continuous. Alright, that is it for proving continuity. You have to prove that all three of these exist. You have to state that all three of these are true to prove that a point is continuous. Let's prove differentiabilities. Key thing to know for proving differentiabilities is that a function can only be continuous. F of x can only be continuous. F of x can only be differentiable. If it is continuous. So if a point does not satisfy these three criteria, that is definitely not differentiable. And only if it is continuous, then it might be differentiable. So differentiable means you can take the derivative of it. And to prove that function is differentiable, you have limit as x approaches h from the left of the derivative. So yesterday we talked about the formal definition of derivative, and that was yesterday we talked about the formal definition. Today there's another definition called the abbreviated version, and it's pretty much the same, except you can now use at a point instead of at zero, towards zero. Don't worry about it too much. Just know that you don't have to worry about it too much for now. So just know that this is a definition of derivative. X minus h. So the thing here is the same concept as yesterday. It's the changing y on top over changing x, and as h approaches infinitely small, you're gonna end up having derivative. So that's it. So the limit as x approaches a point from the left, and this is a derivative. So the limit of this is technically saying f prime of h from the left. All right, this is what it's saying. This entire limit is saying f prime of h from the left. This must equal to f prime of h, the derivative at point h from the right, which means this function, this limit has to equal the limit as x approaches h from the right of f of x minus f of h over x minus h. Again, both of these are the formal definition of derivative. So this is saying the derivative from the left, this is just saying the derivative from the left must equal to the derivative from the right. And that is how you prove that a point is differentiable. So let's take a look at the example we have over here, right? First, let's prove, so it's at x of 0. Oops, I miswrote here. This is not supposed to be 1, this is supposed to be 0. So x of 0. So the point that we're trying to find here is x of 0. So when we plug 0 in, let's first see if it's continuous, right? If we plug 0 in, so let's first find the limit as x approaches 0 from the left. As limit as x approaches 0 from the left, it is this function. So 0 plus 1 is 1. Limit from x approaches 0 from the right is 0. 0 plus 1 is also equal to 1. So now the limit exists, both left and right are equal to 1, and at the actual point it's also equal to 1 because both of these are equal to 1. So this is continuous. And now let's prove if it's differentiable. So derivative of the left side, derivative f prime of x from the left side, is equal to 2x. Plug 0 in, which is 0. Derivative from the right side, I don't know why it's lagging so much. The right side is equal to 3x squared. Plug 0 in is also 0. So both of these are equal to 0, which satisfies this, which means that it is differentiable at 0. It is differentiable at 0. And because a function can only be differentiable when it's continuous, this also says that at point 0 it's continuous, but you have to write it down as well, just in case. So it's continuous at 0 too. So it's both differentiable and continuous at 0. Let's take a look at the example down here. Same thing, f prime of x. Now, first we find the limit as x approaches left and right. So limit as x approaches 0 from the left. This is the left, it's 0. Same thing, limit as x approaches 0 from the right is also 0. Now we take the limit. So now we take the derivative. F prime of x coming from the left side is 2x. No, is 1. Derivative of x is 1. And f prime of x coming from the right side is 2x. Plug 0 in, which is equal to 0. Now 1 does not equal to 0, which means it does not satisfy this criteria, which means it is continuous as proven because the limit are the same, the limit exists, and the limit is equal to the actual point. So this function is continuous. Where's my arrow? This function is continuous at 0. But because the left and right derivatives at 0 are not equal to each other, as shown here, one is equal to 1 and the other one equal to 0, I don't know where they all went. So this function is continuous at x equals 0, but not differentiable at x equals 0. And so yeah, that's it. That's on how to prove continuities and differentiabilities. Thank you for watching.